Integers, addition, and subtraction. There are many methods that teachers and instructors use to teach students how to add or subtract, but I have found one that I find most useful, and I'm going to teach it to you. That method involves remembering two rules. The first is we're going to be checking the signs of the problem, and based on those signs, we're going to be doing either an addition or a subtraction. So if the signs are the same, we are simply going to be adding the numbers. That's rule number one. Rule number two, if the signs are different, then we're going to be subtracting the numbers. And remember, when you're subtracting, it's just going to be the normal subtraction. So in both of those cases, we want to make sure that we always keep the sign of the bigger number. Always make sure you check the sign in front of the bigger one, and that's going to be the sign of your answer. So let's put that into practice. Let's use question 1 and 2 to practice those two rules. All right, so for question 1, we have a negative and a positive, so different signs. We simply subtract the 2 like we normally would. 5 minus 3 is 2. Now the 5 is bigger and it's positive, so this must be a positive 2. Let's try the second question. We have a negative and a negative, therefore same signs. When the signs are the same, we simply add the numbers. 4 plus 2 is 6. The 4 is bigger, it is negative, so our answer must be a negative. For questions 3 onward, we want to introduce a set of sub-rules, and what those will help us do is clean up the problem. The issue here is we have something that may not be understandable at first glance. What do you do when you have a positive sign right adjacent to a negative? Well, the rules are as follows. If you see a positive sign adjacent to a negative, you can simply rewrite it using a minus. If you see a negative sign on question 4, for instance, right next to a negative, so a negative adjacent to a negative, we can simply change that sign to a plus. So before we can even check if the signs are the same or if they're different, we first of all have to clean it up. So therefore, for question 3, we would rewrite this as 8 minus 13. Well, and now that we've cleaned up the question, we can go forward and ask, hey, are those signs the same or are they different? Well, if there is no sign in front of the 8, we understand it to be a positive. So that's a positive and a negative, so different signs, which means we're going to be subtracting these. 13 take away 8 is simply 5. And 13 is bigger, therefore we will keep the sign of 13 a negative, so this is negative 5. For question 4, we have to clean up the problem by rewriting this as negative 9 plus 9. So now the signs are different. We're going to be subtracting. So 9 minus 9 is simply 0. For question 5, rewriting it is negative 25 minus 20. Same signs, which means we add these numbers. 25 plus 20 is 45. 25 is bigger and it's negative, so negative 45. For question 6, we have to clean it up. It's negative 1 plus 13. Different signs, which means subtract the numbers. 13 take away 1 is simply 12, and 13 is the bigger one, it's positive, so the answer remains as positive 12. So remembering these rules, you will never again miss an integer question in your life. So once again, if the signs are the same, simply add the numbers. If the signs are different, simply subtract the numbers. In both cases, always keep the sign of the bigger number. Now, in some cases, you'll have to clean up the problem before you can even ask yourselves if the signs are the same or different. So what do? If you ever see a positive adjacent to a negative, simply rewrite it using a minus. And if you see a negative next to a negative, simply rewrite it using a plus. Once you clean up the problem or rewrite it, then you can ask yourself this and proceed to complete the question. Integer multiplication and division. In this lesson, we'll learn how to multiply and divide integers. And the reason why these operations appear on the same lesson is because the rules for multiplying integers is exactly the same rule as for dividing integers. Therefore, if you know one, you automatically know the other. So let's get started. When you're multiplying integers, we need to remember two rules. A positive times a negative will always give you a negative. The second rule, a negative times a negative will always give you a positive. And we can actually add a third subrule, which is if you have an even number of negatives, the answer will be positive. In other words, if you have 1, 2, 3, 4 negatives being multiplied together, the answer will be a positive. If you have an odd number of negatives, for example, 1, 2, 3, 4, 5 negatives being multiplied together, the answer will always be a negative. So just to kind of quickly recap, an even number of negatives will always be a positive number. An odd number of negatives will always be a negative number. With that knowledge in mind, let's go ahead and try these 4 questions. The first one, we only have one negative, so we know that this is an odd number of negatives. Therefore, it's negative 10. 2 times 5 is 10, negative 10. The second question, we have a negative here and a negative here. Well, 2 negatives become a positive. So negative 3 times negative 4, simply positive 12. Third question, we have 3 negatives. So by the rule we just talked about, we know an odd number of negatives will be a negative. But let's see why that actually happens. So let's go in order. Negative 3 times negative 1 is positive 3. And then I'm just going to bring down the negative 7. And then we'll see that the negative 3 times the negative 7 is negative 21. Last but not least, we have 4 negative numbers being multiplied together. Remember the rule? If you have an even number of negatives, the answer ends up being a positive. And the reason why that works is as follows. Negative 2 times negative 1 is positive 2. Negative 3 times negative 2 is positive 6. And now we just have 2 times 6, and the answer to that is 12. You could do it the way I've done it, or alternatively, you could simply go left to right. Negative 2 times negative 1 is positive 2. Positive 2 times negative 3 is negative 6. Negative 6 times negative 2 is positive 12. So either way, you still end up with a positive. Bottom line, odd number of negatives, the answer is still a negative. Even number of negatives, the answer is positive. Fractions introduction. Fractions are basically a representation of numbers where you have a top part known as a numerator and you have a bottom part known as a denominator. There are 3 types of fractions: proper, improper, and mixed numbers, also known as mixed fractions. Proper fractions are where the top number, the numerator, is smaller than the denominator. An example, 3/5. Improper fractions are where the numerator is bigger than the denominator. An example of that may be 7/3. Mixed numbers or mixed fractions have a whole number component, for example, 6, and a proper fraction attached to them, for example, 2/3. You can convert between the forms, between mixed numbers and improper, and vice versa. So let's actually use this mixed fraction from here and practice how to convert a mixed number to an improper fraction. I'm just going to copy it down, 6 2/3. It's quite simple. You simply multiply these 2 digits, and whatever their product is, you add it to the top number here, the numerator. So 3 times 6 is 18. 18 plus 2 is 20/3. Let's do another one just for practice. So we have 5 2/7. Once again, we'd be multiplying these 2 digits and whatever their product is, add it to the top number here. So 5 times 7 is 35. 35 plus 2 is 37/7. Say we were converting improper fractions to mixed numbers. That's basically undoing what we just did. So I'm just going to borrow this 20 over 3, and we're going to use it to go back and forth. So to convert from improper to mixed, simply use long division, where the numerator goes inside of the division symbol, and the denominator is your divisor. It goes on the outside. So we just ask ourselves, how many times can 3 go into 20? Well, the answer to that is 6. 6 times 3, 18. Subtract these, the remainder is 2. And the way this works is the top number here is your whole number. The remainder is your numerator, and your divisor is your denominator. So 6 2/3. But of course, we already knew that because that was the question from the previous problem. 6 2/3 is the same thing as 20 over 3. Lesson here is you can go between forms, between a mixed number and improper, and vice versa. Now that we know what fractions are, let's go ahead and figure out how we can add and subtract fractions. The one thing that we must keep in mind is fractions can only be added or subtracted if and only if they have the same denominator. So let's look at question 1. We have denominators of 5 and 5. So in this case, we can simply go ahead and add. And you add as follows. Just add the numerators. 2 plus 1 is 3. And you never add the denominators. We just keep it. So it's just going to be 3/5 for that first one. For the second one, again, we have a common denominator of 9. Therefore, we just go ahead and do what it says. 7 minus 4 is 3. And 9 will just be brought over because we never subtract denominators. We just keep the denominator as is. Before we move on to the third question, I want to take a moment here to remind you that you should always simplify your answers to the lowest form. 3/9 can be simplified to 1/3 because they have a common factor. The greatest common factor for 3 and 9 is 3, which means you can divide both of these by 3. So the final answer would be 1/3 for question number 2. So remember to always simplify a fraction to their lowest form. Question 3, when you look, you will find that we do not have a common denominator, and this time we can't just go ahead and add them. Our first goal is to find the least common denominator. That means the smallest number that both 2 and 3 can go into. Well, the smallest number that both of those have in common is 6. So we have to figure out how to make this 3 a 6 and how to make this 2 a 6. And that's going to be done pretty simply. To make this 3 a 6, we have to multiply it by 2. And if you multiply the denominator by 2, then you have to also multiply the numerator by 2, which means we now have a new fraction, 4/6. For the second fraction, we need to make this 2 a 6, and we can do so by simply multiplying it by 3. If you do that to the denominator, you have to do that same thing to the numerator. So we now have a new fraction, and it is 3/6. And these were being added. So 4 plus 3 is 7. Once again, keep the denominator as is. We can leave the answer in improper form, or we can convert it to a mixed number, which is 1 1/6. If you've forgotten how to convert the improper fraction to a mixed number, just refer back to the first video on fractions. The fourth question is, again, one involving finding the least common denominator. So our denominators are 6 and 3, which means we cannot just go ahead and subtract these fractions. We first must find their least common denominator. Well, what is the smallest number that both 3 and 6 go into? Well, that number once again happens to be a 6. So you'll find that for the first fraction, since we already have a 6, we will not do anything to it. However, on the second fraction, we have to make this 3 a 6. So how do we do that? Well, we have to multiply by 2, and if you do that on the denominator, then you have to do that same thing on the numerator, resulting in, well, the first fraction is still the same. The second one becomes 4/6, and now we can simply subtract. 5 minus 4 is 1, over, keep the denominator, it's 1/6. For question 5, Adding mixed numbers is pretty much the same process, except for we have an additional whole number part to worry about. So we'll just go ahead and first of all figure out the LCD. For 11 and 8, the least common denominator for those is 88. So we have to make this 11 and 88 by multiplying it by 8. If you do it on the bottom, you have to do it on the top. And we have to make this 8 and 88, and to do so we have to multiply that by 11. If you do it on the bottom, you have to do it on the top. So we now have new fractions, which is 2 and 40 over 88 plus 4 and 33 over 88. We can now just add the whole numbers, which is 2 plus 4, and that's just going to be 6. And then lastly, we'll add the fraction parts. 40 plus 33 is 73 over 88, and that will be our final answer for question 5. For question 6, we can use a slightly different technique to subtract these fractions. We don't always have to keep the mixed fractions as mixed fractions. We can convert them to improper and then either add or subtract. Just basically do what the question is asking you to do. For question 6, let's convert the 5 1/3 to an improper. Remember from the previous lessons, 3 times 5, and then whatever that is, you add it to the 1. So 15 plus 1 is 16 over 3 minus 2/5. Now we need to find the least common denominator for the 3 and the 5. It is 15. We have to make this 3 15 by multiplying it by 5. If you do it on the bottom, you have to do it on the top. You have to make the 5 a 15 by multiplying it by 3. If you do it on the bottom, you have to do it on the top as well. Therefore, we'll have 80 over 15 minus 6 over 15. 80 take away 6 is 74 over 15. We want to convert this to a mixed number. Therefore, 15 goes into 74 4 times. 4 times 15 is 60, so the remainder is 14 over 15. And that would be your answer for question 6. Multiplying and dividing fractions. There are 2 ways we could approach the multiplication of fractions, and we'll look at both, starting with the more complex method, and then we'll take a look at the shortcut. So let's use question 1 as our example. The longer method is simply multiplying the top numbers. 4 times 5 is 20, and then simply multiplying the denominators. 5 times 8, which is 40. And then we always make sure that we simplify our fractions to the lowest term. So 20 and 40 can be reduced because they have a greatest common factor, which is 20. We can divide each of these by 20, which results in 1 over 2 as our final answer. That would be using the longer method. We could rework this question, as I'm going to erase the previous answer. And instead of multiplying across, we are going to use the cross-canceling method. Cross-canceling simply means you're going to be looking for a number that's on the numerator and try to figure out if it has a common term, the greatest common factor, and you can reduce by that. So let's once again work question 1. 4 and 8 do have a greatest common factor. We can simplify those by 4. 4 goes into 4 one time. 4 goes into 8 twice. Also, the 5 and the 5 can be simplified because the greatest common factor is 5. 5 goes into 5 once. 5 goes into this 5 once. And now what we have left is 1 times 1 up top. And on the bottom, we have 1 times 2, which is again 1/2, like we found in the previous question. The reason why you might want to really master the cross-canceling method is because you will sometimes have really big fractions that take too much time to multiply by hand, and it would be really beneficial and useful if you can make those numbers smaller through cross-canceling. Let's try another question, and just for the sake of teaching the shortcut and the more effective way of working this, we're going to stick to the cross-canceling method. Now, when you're multiplying fractions, you cannot use mixed numbers. So for question 2, Our first goal is to convert the 1 2/3 to an improper fraction. And just remember, this is simply done by multiplying these numbers and then adding their product to the numerator. So 3 times 1 is 3, 3 plus 2 is 5. This becomes 5/3 times 1/10. Now, let's look for cross-canceling opportunities. We can simplify the 5 and the 10 for sure. 5 goes into 5 once, 5 goes into 10 twice. So the result is 1 times 1 up top and 3 times 2, 1/6 for question 2. For question 3, we have to convert these mixed numbers into improper fractions. The good news, they're the same, so we really just have to do one and copy it over. 2 times 1 is 2, 2 plus 1 is 3, so each of these will be 3/2. This time, nothing cancels. We don't have anything cross-canceling, so we just multiply. The top becomes a 9, the bottom becomes a 4. And to convert this improper to a mixed number, we use long division. Well, 4 goes into 9 2 whole times. The remainder is 1, and we just keep the denominator. And that pretty much completes how you multiply fractions. Now, division is just an extension of multiplying. So much so that we have come up with a mnemonic to help us remember what to do. When you're dividing fractions, you keep, change, flip. What that means is you keep the first fraction as is, change the division sign to a multiplication, and you always flip the second fraction. Keep, change, flip. And now that we've done that, all we need to do is look for cross-canceling opportunity. In question 4, we do have it because 9 goes into 9 once, 9 goes into 9 once. 2 goes into 2 once, 2 goes into 4 twice. So now that we've cross-canceled, we just multiply. Up top, we have 1 times 1, which is just 1. On the bottom, we have 1 times 2. So the answer is just 1/2. So for question 5, remember we cannot work with mixed numbers. When you're multiplying or dividing, we always convert them to improper fractions. So we'll do that for question 5, converting 1 and 5, 6. 6 times 1 is 6. 6 plus 5 is 11. So 11/6. Change the sign to multiplying. Flip the second fraction. We once again keep, change, flip. Now, do we have any cross-canceling opportunity? Yes. 3 and 6 can cross-cancel, so the 3 goes into 3 once, 3 goes into 6 twice. Also, the 11 and the 22 can cross-cancel. 11 goes into 11 once, 11 goes into 22 twice. So we are left with 1 times 1 up top and 2 times 2, which is 4. So the answer for question 5 is simply 1/4. Question 6 is what you might hear referred to as a complex fraction, because we have a fraction over another fraction, and it's just a weird way to view a division. But don't worry, you can always rewrite the problem in a way that makes more sense, or a way that you're accustomed to seeing. So 2/3 divided by 4/5, and this looks familiar. It's a lot like question 4 and 5 from above. So we just do what we've done so far. We've kept the first fraction, changed the sign to multiplying, and flipped the second fraction, the keep, change, flip. And once again, we'll look for cross-canceling opportunity. Yes, we have it, because 2 goes into 2 once, 2 goes into 4 twice, and all that's left up top is 1 times 5 is 5, over 3 times 2, which is 6, which makes 5/6 the answer to this problem. Now, there's a second way we could approach and work this problem out, which doesn't involve rearranging it. So I'm going to show it to you, and all you do is simply multiply the two outside terms, and you set those as your numerator, and then multiply the two inside terms, and you set those as your denominator. So we can call this our outer over inner method. And the reason why you might want to learn this is because it saves time. Remember, these exams are time pressured. However many seconds you can shave off, it only can serve to your benefit. So let's go ahead and do this. Outer, we have the 2 and the 5, so 2 times 5 is 10, over the inner, which is 3 times 4, and that's 12. Of course, we do have to simplify this, so the answer, just like we found in the first problem, is 5/6. Same answer, a lot quicker. Order of operations using PEMDAS. In this lesson, you learn what PEMDAS is and how to use it. And by the end of this lesson, you should be able to simplify and evaluate expressions like the ones you're seeing on this screen. PEMDAS is simply a mnemonic which helps us remember the order in which we are supposed to follow anytime we are working out an expression that has more than one operation. I know that's a lot of math jargon, so let's just break it down to its smaller parts. Expressions are any of these things that you see on this screen. Each of those can be called expressions. Operations are simply the signs, the symbols that you're seeing on here. Math has 4 operations: addition, subtraction, multiplication, and division. So anytime you have an expression that has more than one operation, we have to follow PEMDAS. It simply tells us, hey, look to see if you have any parentheses. If you do, work the parentheses first. Next, work on exponents. Third, multiply. Fourth, divide, so on and so forth. So for question number 1, let's go ahead and try to follow PEMDAS. Do we have parentheses? Yes. 6 minus 4 is simply 2. Then we bring down everything else that we haven't yet touched. So I'm going to bring down the 49, divide by 7. Do we have exponents? No. Multiplication? Yes. 2 times 49 is 98, divided by 7. Next, division. 98 divided by 7 is simply 14. The second question has more operations, but not to worry, because that's what PEMDAS will help us sort out. Do we have parentheses? Yes. So we start there. 2 plus 1 is 3, but then notice that that is raised to the second. So let's just bring back down everything else that we haven't yet used. So 35 divided by 5 minus that times the 4. Do we have exponents? We sure do. So we'll bring back the 35 divided by 5 minus 3 squared, which is 9. We've worked out the exponents. Next is multiplication, which we do have. So 9 times 4 is 36. And we bring down everything else that we haven't touched. We do have division for this problem. 7 subtract 36. And you'll find that the answer to this is negative 29. The third question has a subtraction and then an addition. Now, a big deal and a big rule that I did not mention at the beginning is sometimes you disregard PEMDAS. This is certainly one of those instances when you do not follow PEMDAS verbatim. So if you ever have a question that has subtraction and addition only, ignore the rule and simply go left to right. Let me repeat that. If a question only has subtraction and addition in it, you can ignore PEMDAS. You should ignore PEMDAS and simply go left to right. So for this question, we would do 5 minus 3, which is 2, and then just bring down the 7. 2 plus 7 is 9. Likewise, if a question only has multiplication and division, we should avoid using PEMDAS and simply go left to right. Once again, just like we went left to right when we had addition and subtraction, we should also go left to right if a question only has division and multiplication, such as question 4. Although PEMDAS says we should multiply before we divide, we should not obey that rule. Simply go left to right. 16 divided by 4 is 4. I'm going to bring down the 5. 4 times 5 is 20. So let's recap. PEMDAS is simply a mnemonic that helps us remember the order in which to evaluate expressions, specifically expressions that have more than one operation. There are 2 instances that we should ignore PEMDAS and simply go left to right. The first one, if a question only has addition and subtraction, simply go left to right, even if subtraction comes first. The second scenario is when a question has division and multiplication only, ignore PEMDAS and simply go left to right. It doesn't matter if the division comes first. And in doing so, you will make sure that you get every question that requires order of operations correct. Properties of exponents. Well, first let's talk about what exponents are. I'm sure you have seen numbers such as 3 raised to a certain power with a little number or digit slightly placed above it. That is what you might call an exponent. This number 4 is what's called an exponent, and the 3 is what's known as the base. So, before we can even go to the properties, let's just examine what you would do to figure out what 3 to the 4th power is. Just remember the 3 to the 4th power means you're going to take 3 and multiply it to itself 4 times. And the answer to that would be 81. Since the exponent 4 is a relatively small number, we can work these problems without an issue. But the problem arises when you have really, really big exponents. For example, 3 to the maybe 56th times 3 to the 81st. And can you imagine writing out 56 threes and multiplying those to 81 threes? It becomes a little bit of a problem. So enter the properties of exponents that give us a way to represent exponents in a much friendlier way. So for the base, I'll just use the variable. I'll use a letter for the base. Let's say our base is m raised to the 4th power multiplied to m raised to the 5th power. Now, when you're multiplying numbers that have the same base, in our case, the base here is m, you simply add the exponents. So our answer to this would be m to the 9th, because 4 plus 5 is 9. On the division property, let's say once again, I'm going to use m. We have 13 over m to the 10th power. When you're dividing numbers that have the same base, you keep the base and you simply subtract the exponents. Always subtract the bottom exponent from the top one. So in this case, it would be 13 minus 10, which makes this m to the 3rd as your answer. The next property is the power to power, whereby if you have m to maybe to the power of 5 raised to the 3rd power, a power raised to a power, you simply keep the base, and this time you would be multiplying the exponent. So this would be 5 times 3, which makes m to the 15th the answer to that. Last but not least is the zero property, which is probably one of the easiest things you'll learn. Anything raised to the power of 0 will always equal 1. Now there are reasons why that happens, which we will not be covering in this video, but maybe we'll talk about that later in upcoming videos. One other thing that is worthy of mention is the rule that you should never ever leave your answer with a negative exponent. You should always strive to make any negative exponent a positive. The good news, it's really easy to do. And let me just illustrate that using an example. Say we have 3b raised to the negative 5 over, say, 7. We cannot leave the answer in this format because we have a negative 5 exponent. Fixing it, once again, is easy because you simply take whatever is negative and you move it. If it's on the top, you will move it to the bottom. If it's on the bottom, you would move it up top. So for this question, we would now have 3. We are moving this b to the negative 5 downstairs to become a denominator. So I'm going to keep the 7. Then we have b, but now that we moved it, it's got a positive 5 exponent. Let's do another one. Say we've got 2m to the negative 5, b to the 6th over 3x to the negative 2. To fix this, we simply need to take every negative exponent and move it. So this would need to come downstairs, and this would need to come upstairs. So then we would end up with 2b to the 6th, x to the 2nd, all of that over 3m to the 5th power. Radicals, addition, and subtraction. But before we can get to adding and subtracting radicals, let's just review. Radicals are basically symbols. For example, square root of 16, the root this part is a radical. The 16 is what's called a radicand. In other words, anything that is inside of a radical symbol is called a radicand. Now, the way square roots work, you have to figure out what number times itself twice gives you the radicand. So if you're looking at 16, the question really is, what number times itself will give you a 16? And that number is 4. Therefore, the square root of 16 is just 4. Say, for instance, we had a cube root of, say, 27. The question here would be, what number times itself 3 times, because the root is 3, gives you a 27? And the answer to that is 3, because 3 times 3 times 3 is 27. So on and so forth. So let's just attempt the questions that we have on here. The first one we've already answered. The square root of 16 is simply 4. The second question is the square root of 28. Well, there's a bit of a problem because 28 is not a perfect square. In other words, no number times itself gives you 28. So we have to break down this 28 and simplify this radical. The way to do this is to find 2 factors that when multiplied will give you 28. What numbers do you multiply to get 28? We don't want just any random numbers. One of those factors has to be a perfect square. So let's go over every number that multiplied gives you 28. For example, 2 times 14 is an example. However, neither the 2 nor the 14 is a perfect square, so that's not a good option. Let's go to the next pair that when multiplied gives us 28. How about 4 times 7? And yes, this is a good pair because 4 is a perfect square and the 7 does not have any perfect squares in it. It's prime. So we can break down the 28 into 4 times 7. And of course, that's still inside of the radical. We haven't changed the problem because 4 times 7 is still 28. We just rewrote it to where we can now simplify. The way to simplify this, well, 4 has a square root. So the square root of 4 is 2. The 2 goes on the outside. 7 does not have a square root, so it's going to remain inside. So square root of 28 simplified is 2 root 7. Next question is the square root of 432. 432, once again, is not a perfect square. So we have to come up with factors that when multiplied will equal 432. And just as a reminder, we can't just take any 2 random factors. We have to make sure that one of our factors is a perfect square. So what multiplies to 432? What pairs? Well, starting at 2. 2 times 216. Well, neither of those is a perfect square. So we'll throw that out. Check for 3. 3 goes into 432 144 times. And that is a good pair because 144 is a perfect square. 144 has a square root. So we can rewrite the 432 as 3 times 144. And now we just take the square roots. 3 doesn't have a square root, so it's going to remain inside, but 144 does. Square root of 144 is 12, so the 12 is going to be on the outside. 12 root 3 is the simplified version of square root of 432. Adding and subtracting radicals can only be done if we have the same radicand. In other words, we can only add and subtract radicals if the number inside of the root is the same. For this question, we can actually go ahead and add. And be careful how you add these. We never actually add the radicands or the radicals. We only add the whole numbers. So in this case, that 4 and the invisible 1 that is in front of this root 2. Those are the only 2 things we add. We would keep the radical 2. So 4 plus 1 is simply 5. and we keep the radical. So the answer to this is 5 root 2. For the next question, we can't subtract these just yet because we don't have the same radicand. However, because we've learned how to simplify radicals, let's see if we simplify root 75, we'll end up with a root 5, which would then allow us to subtract them. So focusing on the root 75, well, what two factors multiply to equal 75? We've got 3 times 25. Oh, and that is a great pair because 25 is a perfect square, and we can factor it out. So here we still have the negative 3 root 5 minus 2 root 3 times 25. Square root of 25 is 5, so the 5 would come out. And once it does, you multiply to the 2 that is already existing out there. So we still have the negative 3 root 5. Now we would have negative 10 root 3. Unfortunately, we didn't end up with the same radicand, which means we can't subtract these. We'll just leave this as our final answer. And for the final question, we've got 5 root 5 plus 2 root 96 minus 20 root 24. We need to see if we can simplify these to get them to be the same radicand. So the 5 is already in the lowest term, so we will not mess with the 5. I'm just going to copy it down, 5 root 5. The 96, however, can be broken down to 6 times 16, and the 24 can be broken down to 6 times 4. So if we put the root back on these, square root of 16 is 4, so the 4 would go on the outside. The square root of 4 on this one is 2, the 2 would go on the outside. So then we still have the 5 root 5 because nothing changed there. The 4 that went out would multiply the 2 that was already on the outside, making it an 8, and the 6 is remaining, so 8 root 6. On the next term, 2 went outside, so the 2 would multiply the 20 that was already on the outside. 2 times negative 20 is negative 40. And of course, the 6 stays inside because it doesn't have a root. And this time, we have like radicands, so we can actually combine these two terms. To do that, we are going to say 8 minus 40. So we'll keep the 5 root 5. 8 minus 40 is negative 32 root 6. Rationalizing radicals. Before we can actually tackle these scary looking expressions, let's just take a moment to learn how to rationalize simpler versions of radicals. Well, the idea behind rationalizing is we are not allowed to have roots on the bottom. Roots can never be denominators. For instance, if you have a number 5 over square root of 3, we cannot leave it in this form because we have a radical as a denominator, which is not good. So to fix that, we do something called rationalizing. And it sounds fancy, but all rationalizing is simply multiplying by whatever the denominator is, whatever the root is. In our case, it's root 3, so we have to multiply the denominator by root 3. If you do it on the denominator, you have to do that same exact thing on the numerator. Now, in front of this root 3, there's an invisible 1. And just to remind you, when you're multiplying radicals, you can only multiply whole numbers. So 5 times 1 would be 5, and then root 3. On the denominator, we have root 3 times root 3, which is root 9. But then we know that 9 is a perfect square. So the square root of 9 is simply 3. In fact, the whole point of rationalizing is taking advantage of the fact that any root times itself is simply the radicand. So root 3 times root 3 is just 3. Let's try another one. Root 5 times root 5 is square root of 25, which we know is 5. Let's try another one. Square root of 2 times square root of 2 is the square root of 4, which we know is 2. So the whole objective of rationalizing is so you end up with a whole number. Now we're going to take that idea and we're going to just develop it a little bit further. All right, so say we had 5 root 3 over 4 root 5. As a reminder, we are not allowed to have roots on the bottom as a denominator. So we'd have to rationalize that. To do that, we simply need to multiply the denominator by its conjugate. The conjugate, to rationalize this, we simply need to multiply the root 5 by itself, root 5 times root 5. And if you do it on the bottom, you have to do that same thing on the top. What's going to happen is you have this whole number 5 times the invisible 1 right here is simply a 5. And then you have the root 3 times the root 5 is square root of 15. On the bottom, we have this 4. And the root times itself, as we discovered, is just the radicand. So this is just a 5. The 4 times the 5 is 20. You might be quick to consider this being completed, but it is not. Always make sure you simplify the fraction. We have a 5 and a 20. Those have something in common. We can simplify. 5 goes into 5 once. 5 goes into 20 4 times. So the final answer is really root 15 over 4. And now that we've reviewed and prepped for the bigger problems, we can actually go ahead and attempt the first question. Here, the denominator is a term. It's 2 minus root 3. In fact, it is highly recommended that we enclose that term in parentheses. Now, rationalizing a term like this requires you to multiply by its conjugate. Conjugate means same exact numbers, for example 2 and root 3, but you change the sign in the middle to the opposite. So for this one, the conjugate of 2 minus root 3 is actually 2 plus root 3. And if you do that to the denominator, then you have to also multiply that number to the numerator as well. And now we need to open up these parentheses using the distributive property as shown. 2 times 2 is simply 4, and 2 times root 3 is simply 2 square root of 3. Remember, we can't multiply whole numbers by the root, we just list them. On the denominator, we have to FOIL. Foiling means multiplying this first number to both of those. So we would have 2 times 2, which is 4. 2 times root 3 is 2 root 3. Then we would multiply this second number by both of these again. Negative 3 times 2 is negative 2 root 3. And then negative root 3 times positive root 3 is simply negative 3. Now when you look closely, you'll find that these are like terms and they simply cancel out because 2 root 3 minus 2 root 3 is simply 0. So those are gone. And we are left with 4 minus 3, which means our new denominator is 1. And the numerator hasn't changed. We have 4 plus 2 root 3. In fact, we don't need the 1 underneath this because anything with a denominator of 1 is itself. So I can just erase this and just have 4 plus 2 root 3 as the answer to this. For the next question, we'll do the same exact thing as we did for the previous one, which is to rationalize. But before we even start, let me enclose these terms in parentheses. That way it's going to be easier to see how to multiply them. And now finding the conjugate of the denominator is super simple. So remember, the conjugate is just changing that sign that is between the two terms. The conjugate of this then will be negative 7 minus square root of 2. And if you do that to the denominator, you have to do that same exact thing to the numerator as well. So the next step is foiling. And all that means we're going to be taking this negative 5 and multiplying it into this parenthesis. So negative 5 times negative 7 is 35. Negative 5 times negative root 2 is positive 5 root 2. And then once we finish that, we can go on to the next digit, which is root 3 times negative 7. That makes it a negative 7 root 3. And now we've got root 3 times negative root 2, which makes it a negative square root of 6. Now the denominator, we've got negative 7 times negative 7, which is simply 49. And we've got negative 7 times negative root 2, which is simply plus 7 root 2. And then we've got root 2 times negative 7, which is negative 7 root 2. And we've got root 2 times negative root 2, which is simply minus 2, because any root times itself is just the radicand. On the denominator, you'll see that we've accomplished our goal, which was to get rid of the radical. It happens because 7 root 2 minus 7 root 2 is 0, so the radical is gone. They cancel out. However, we are left with a 49 minus 2, so the new denominator is 47. On the numerator, we can look and scan to see if we have any like terms, but this time we don't have any. This is a root 2, this is a root 3. Remember, we can only add or subtract if we have the same radicand. Since we don't, there's nothing we can do to this numerator. So we'll just copy it down exactly as is. So 35 plus 5 root 2 minus 7 root 3 minus square root of 6 would be the answer to this question. Complex numbers, imaginary number I. We've seen from previous parts of this video, of this course, that we can square root numbers. When we talked about radicals, we found that the square root of a number 4 is simply what times itself gives you that number. So the square root of 4 is 2. What we didn't talk about at the time is that 2 is not really the entire answer. The full answer for square root of 4 really is plus or minus 2. The reason why that's the case is because there are two ways to end up with a 4. Now, if you took 2 times 2, you would see that that is 4. Also, if you took negative 2 times negative 2, the answer is also 4. So when you square root a number, you should account for both ways on how we can end up with a radicand. So let's just try another one of these. If you took the square root of 64, what times itself gives you 64? Well, it's 8. But again, we have to account for both the positive and the negative. So the answer to this would be plus or minus 8, the full answer. On the other hand, what do you do, or how can you find the square root of a negative number? If we had tried to apply that same logic as we did from the previous problem, you would find that it fails, because nothing in the world times itself will be a negative. For example, a negative 2 times negative 2 will always be a positive 4. It doesn't give you the negative 4. Likewise, the positive 2 times a positive 2 will always be a positive 4, which once again is not a negative. So this is a problem that we encounter a lot in math, whereby finding the square root of a negative number is not possible, so much so that it was agreed upon that we can rewrite the negative 4, any negative integer, as follows. You can break it down to negative 1 times 4. The reason why we now involve a negative 1 is because it's a fact that negative 1 square rooted gives you I, and that is where I, the imaginary I, comes from. Now, back to this problem. Since we have already rewritten it, we can now find the square roots. Well, we know the square root of 4 is 2, and we've just found out that the square root of negative 1 is I, so I. And of course, we have the plus or minus. So every time you're trying to take the square root of a negative number, you can rewrite it. So let's practice another question. Say we wanted to find the square root of negative 16. The answer to this would be plus or minus 4i, because we can rewrite the root 16 as negative 1 times 16? Well, the square root of 16 is 4, and the square root of negative 1 is I. So that's our answer. So now that we know that I comes from having the square root of a negative 1, we can now talk about how I is involved and included on both the SAT and the ACT. One of the ways is trying to compute what I squared is, what I to the third, maybe even I to the fourth power. So I squared is simply negative 1. I to the third is simply negative I. And I to the fourth is simply 1. And for each of these, let's just take a moment to explain why the answers are as they are. So starting with this one right here. The reason why I squared is negative 1 is because, well, by definition, I is square root of negative 1, which means we can take negative 1 and multiply it to itself, as shown. Negative 1 times negative 1 is simply negative 1. Recall this from the previous lesson on radicals. Any radical times itself is simply the radicand. So I squared is negative 1. I to the third power is also square root of negative 1 times square root of negative 1 times square root of negative 1. Once again, any radical times itself is simply the radicand. So it would be negative 1 times square root of negative 1. And then we know that the square root of negative 1, as we just found out, is I. Therefore, negative 1 times I is negative I. That's why the answer is negative I for I to the third. Last but not least, for I to the fourth power, it's basically square root of negative 1 times the square root of negative 1 times the square root of negative 1 times the square root of negative 1. Square root of negative 1 times square root of negative 1 is simply negative 1. And the square root of negative 1 times the square root of negative 1 is also negative 1. Negative 1 times negative 1 is positive 1. So for the purpose of both the SAT and the ACT, it would be extremely useful if you remembered these rules. And the reason why we stop right at I to the fourth power is because they repeat themselves after 4. And we'll discuss this later on and show you how this is applied in actual problems involving I when we get to the paid version of the SAT or ACT review course. But for now, this will suffice. Conjugates of complex numbers. In the same way that we weren't allowed to have roots as denominators, we are not allowed to have the number I or the letter I as a denominator. That goes against the math law. So to fix that, we have to remember those few rules that we learned from the previous slide. Now, just to remind you, it is imperative that we remember these. I to the power of 1 is I to the second power is negative 1, I to the third power is negative I, and I to the fourth power is 1. To help you remember those 4, we can use this mnemonic. It goes I1, and you put the negatives in the middle. So the negatives are here and here. Once we establish that, we can attempt these problems. Our goal is to undo, or rather get rid of i's from the denominator. So for the first question, this I has to go away. And the way to do that is pretty simple. Just multiply both the numerator and the denominator by I. So this becomes 6i over I to the second. But remember, we know that I to the second is negative 1. So this is really 6i over negative 1. Well, we can clean this up a little bit. 6 divided by negative 1 is negative 6. So the final answer here really should be negative 6i. The second question is pretty similar to the first one. All we need to do is get rid of this I. The 5 is fine. There's no law against having a number 5 as the denominator. So really our focus here is just to how do we get rid of I? Once again, we multiply the denominator by I. If you do that to the denominator, you have to do that same exact thing to the numerator, which means 7 times I is now 7I over 5I squared. Recall, though, that we know that I squared is negative 1. So really, this is 7I over 5 times negative 1. This is 5 times negative 1. So this becomes 7I. 5 times negative 1 is negative 5. But I would not write the negative on the bottom just because it looks weird. You should write it in the middle or give it to the numerator. So if any part of a fraction is negative, it makes the whole fraction negative. We just don't write the negative on the bottom. We either write it in the middle or you can write it on top. Just don't leave it on the bottom. It just looks weird. For this one, I'll put it on top. So that will be the answer to this second question. The third question is slightly different because the denominator is now a term, which we are going to enclose using parentheses like so. And a lot like we did on the radicals, we are going to have to rationalize this by multiplying it to its conjugate. And yes, if you guess that the conjugate is simply changing the sign in the middle, you'd be correct. So the conjugate of 3 minus I is 3 plus I. And if you multiply the denominator, you bet that you have to do that same exact thing to the numerator. And now we're just distributing. 5 times 3 is 15. 5 times I is 5I. And the bottom part, we are going to be foiling. So 3 times 3 is 9. 3 times I is 3I. Negative I times 3 is negative 3I. And negative I times positive I is I to the second power. So for the denominator, we have a little bit of cleaning up to do. The top part is pretty much finished, but the denominator, we've got the 3I minus 3I that cancels out. And that was the whole objective, to not have I as the denominator, and we've accomplished that goal. Now, remember though that I squared is negative 1. So really this is a minus 1. And we can say 9 minus the 1 is 8. So our new denominator here is 8 with a numerator of 15 plus 5I. The final question is a lot like the previous one, whereby we have a denominator that has I, therefore we have to multiply by its conjugate. The conjugate of that number is negative 4 minus 2I. And if you do it to the denominator, you have to do that same exact thing to the numerator as shown. Next, we are just foiling, which means we're going to take this negative 2 and multiply it through. Negative 2 times negative 4 is simply 8. Negative 2 times negative 2I is simply 4I. Negative I times negative 4, and then negative I times negative 2I. Negative I times negative 4 is positive 4I. And negative I times negative 2I is simply positive 2I to the second. Now we finished the numerator, we can focus on the denominator. Negative 4 times negative 4, and then negative 4 times negative 2I. Negative 4 times negative 4 is simply 16. Negative 4 times negative 2I is plus 8I. Next will be 2I times negative 4, and then 2I times negative 2I. 2I times negative 4 is negative 8I. 2I times negative 2I is negative 4I to the second. Good news is that the 8I and the 8I will cancel, which was our goal. Since we can't have I as a denominator, 8I minus 8I cancels out. So we are left with 8. Also notice that at the top we have like terms. So 4I plus 4I is actually 8I plus 2I squared. And the denominator is now 16 minus 4I to the second. However, we've discovered in previous problems that I squared is actually a number. So I squared is negative 1. So this really is 2 times negative 1. Also, we have an I squared here, which is again negative 1. So this is really negative 4 times negative 1. So we can rewrite these as 8 plus 8i minus 2 over 16. Negative 4 times negative 1 is positive 4. 16 plus 4, which simplifies further because the 8 and the minus 2 can be simplified. 8 minus 2 is 6 plus 8i over 16 plus 4, which is 20. However, we shouldn't be so quick to rule this as our final answer, because if you look closely, you'll find that the 6, the 8, and the 20, they have a greatest common factor. There's a number that goes into all of them. That number is 2, which means we can reduce this by 2. Therefore, 2 goes into 6 3 times, 2 goes into 8 4 times, 2 goes into 20 10 times, and that makes the final answer 3 plus 4i, all of this over 10. Welcome to this lesson on linear functions. In this lesson, we'll talk about the 3 different ways we can express linear functions. Those 3 ways are slope-intercept, standard form, and point-slope form. In each of those, we will explore and take a look at what the variables mean. In some forms more than others, the variables mean something special. And without further ado, let's go ahead and get started. So, in slope-intercept form, which is expressed as y equals mx plus b, we see that there's the letter m, and m stands for slope. Slope is basically the steepness of a line, and we define that as rise over run. So slope is basically a fraction. It's got a numerator, rise, and a denominator, run. And then the next thing we want to look at, the next variable, is b. B is the y-intercept. Basically, what a y-intercept is, it's the point at which any graph crosses the y-axis. So let's say we have an x and y plot like this one, and we drew a line, let's maybe call this 4, and we drew a line straight through, and it crosses at 4, well, then 4 would be our y-intercept. So if an equation is written in slope-intercept form, we can easily identify what the slope is, that is the steepness of a line, and also identify its y-intercept. For example, if we have an equation in slope-intercept form written out this way, y equals maybe 2/3 x plus 3, then we would know that 2/3 is our slope and 3 is our y-intercept. The reason why both the 2/3 and the 3 are important is because if you were trying to graph, we would know to start at the y-intercept. That is a really important point to have. If you're graphing on an x and y plane, the y-intercept is your starting point. So you would want to put a dot, your first point, right at 3, where the graph crosses the y-axis at 3, and then you would use your slope to figure out where to put the next point. Remember, slope is rise over run. So in our case, the slope is 2/3, which it tells us to rise 2 places and run 3. So from our first point, which is the y-intercept, we would rise 2 places, 1, 2, and then we would run 3 places, 1, 2, 3. That's where we would put our next dot. And then, of course, you can join those lines and you have yourself a line, the graph of y equals 2x plus 3. So with slope-intercept form, it's really, really important to understand that m stands for slope. The slope is the steepness of a line. It's got a rise and a run. It's basically a fraction. And b is the y-intercept, which is the starting point of the line if you were to graph it. The next form of linear functions is standard form, whereby we have the x and the y on the same side of the equal, and then the c value, which is the constant. Constant just means a number, is on the right side of the equal sign. An example of what this might look like is 3x plus 2y equals 4. And 2 main rules that we have to remember in standard form: x cannot be a negative ever. So you have to make sure if you're rewriting you don't leave the x as a negative number. Also, we can't have any fractions, so no fractions. So those are the only two rules, stipulations that are given to us when it comes to writing linear functions in standard form. The third form of writing linear functions is the point-slope form, and it's pretty similar to the slope-intercept because it involves having a slope, but it does not have the y-intercept. So you'll find that this m, just like we saw in the slope-intercept form, stands for slope. And once again, just as a reminder, slope is basically a fraction. It's got a numerator, the rise, and a denominator, the run. And it basically tells you the steepness of a line. Other than that, we have y1 and x1, both of which have to be numbers if you're going to write an equation in point-slope form. So let's take a look at what an equation. So let's take a look at what an equation in point-slope form would look like. I'm going to make up one. So we have y minus 3 equals 6, open parenthesis, x minus 2. This will be an example of an equation in point-slope form. In all the cases, notice that y and x are always left as variables. Every other letter, every other variable needs to have a number in place of it. This lesson is on linear functions, converting between the different forms that we've learned from the previous one. And we'll start off by converting slope-intercept to standard form. The first thing we'll do is write out the destination. What do we want to do? Well, we're trying to rewrite it into standard form, so it might be helpful to write out what we are trying to accomplish like so. So basically, we want to make sure that we have x and y on the same side of the equation, and the constant, which is 2 in this case, will be on the right side on its own. Now, before we get started, I do want to remind you of the two stipulations that we have to keep in mind when you're writing out an equation in standard form. The first one was x must be positive. In other words, we can't have a negative x. Okay. And the second one was no fractions. So with that in mind, let's go ahead and get started. We want to get the x and y on the same side. That means this negative 1/4 x needs to go to the left side. And we can do that by doing the opposite, the inverse. So add 1/4 x. If you add it to the right side of the equal, we have to add it to the left side of the equal sign to keep things in balance. Those cancel because negative 1/4 plus 1/4 is gone. Now we can just list these as 1/4 x plus y equals 2. And now we can list this as 1/4x plus y equals 2. So we're getting closer, but remember, we were told that we cannot have fractions. So we need to get rid of this denominator 4 right here. And the way to do that is by multiplying this entire equation by 4. So we are distributing 4 all the way through. We're going to write the result of it here. So 4 times 1/4 is simply 1x. 4 times y is 4y. And 4 times 2 is 8. Therefore, we have completed it. The second question is asking us to convert this equation from standard form to slope-intercept form. Once again, it's nice and wise to write out the destination of what we are trying to accomplish. So slope-intercept is y equals mx plus b. This time we don't have any stipulations, so we can dive right into it. That means y needs to be isolated. It needs to be by itself. We have to get rid of this 5x then. We do that by doing the inverse again, which is subtracting 5x. If you do it on the left, we have to do it on the right side as well. 5x minus 5x cancels out, which is our goal. Negative 2y equals negative 5x plus 6. I'm just going to write them in the correct order. Now we are closer to getting y by itself, but there's this negative 2 that we need to get rid of, and then we'll be truly done. So right now, the negative 2 and the y are separated by a multiplication sign. So the inverse of multiplying is dividing. So we're going to divide every single term by negative 2. I'm going to just move this up here so we have more room. The answer to this will be y, because the negative 2 and the negative 2 cancel, equals negative 5 over negative 2. We want to leave that as a fraction. Again, remember, a negative divided by a negative is a positive. So that's just 5 over 2x. And then 6 divided by negative 2 is negative 3. That would be the answer to the second problem. Last but not least, we're going to be converting this linear function from point-slope form into slope-intercept, just like we did in the previous two problems. Let's write out the destination. We are trying to write an equation that looks like this: y equals mx plus b, which means we need to isolate y. In other words, get y by itself. To achieve this end, we have to start off by distributing this negative 1/4 into that parenthesis. And the result of that will be, well, the left side still has the y minus 3. On the right side, we have negative 1/4 times x, simply negative 1/4 x. Negative 1/4 times 4 is simply negative 1. We are closer to getting our end goal. Now that we are closer to arriving at our destination, we just need to take one last step and we'll have y by itself. This 3 is standing in the way of us achieving our goal, so we need to get rid of it. Right now it says minus 3, so we have to do the inverse, which is plus 3. If you add 3 to the left, you have to add 3 to the right side as well. So negative 3 plus 3 is 0. Those cancel out. Therefore, y equals negative 1/4 x. And then we've got negative 1 plus 3, which is just positive 2. And we have achieved our goal. We could take this a step further and convert this slope-intercept equation into standard form. In fact, let's practice that some more. Remember, standard form is ax plus by equals c. No fractions. And x cannot be negative. It must be a positive number, in other words. So let's copy it down. We have y equals negative 1/4 x plus 2. First thing we'll do is try to get x to the left side. So we add 1/4 x. If you do it to the right, you have to add it to the left side as well. So we now have 1/4 x plus y equals 2. Because we are not allowed to have fractions, we have to get rid of this denominator 4. And to do that, we just need to multiply this entire equation by 4. 4 times 1/4 is simply 1x. So I'm going to write that as x. 4 times y is 4y. And 4 times 2 is 8. And now we've accomplished our goal again. So we rewrote this equation from point slope into slope intercept, and then we took that and wrote it into standard form. So as you can see, you can go between forms as you please.